It's my pleasure to introduce our keynote speaker, James Bell. James is the head of artificial intelligence and machine learning customer solution engineering at Dow Jones. He's recognized as one of the top 250 IT leaders in the UK, an international public speaker, and a published writer on topics such as alternative data, risk and compliance, and AI ethics. He's worked in financial services for 20 years, providing leadership in AI, risk and compliance, payments technology, business consultancy, and IT management. He's built, developed, and led multiple teams and engagements all over EMEA, MENA, and APAC regions of the world, and developed a unique understanding of client needs. James will discuss using advanced technologies to drink from the fire hose in his dynamic address. Please feel free to participate by posting your questions and comments for James in the comments section, and I'll present them during our Q&A following his address. So let's welcome James Bell.
Hello everyone, my name is James Bell and I'm the head of AI and machine learning for the Dow Jones Customer Solution Engineering team. Thank you for coming today to my presentation of Drinking from the Fire Hose. So let's consider the schedule and you can plan your time accordingly. We'll very quickly start by considering what we mean by AI and indeed the fire hose. We will then look at some of the major problems with attempting to metaphorically drink from it using my strategy for combating this problem and some best practices. Finally, we'll come to two case studies, both showcasing how to understand large data about events. One for analysis purposes and another for predicting, as Donald Rumsfeld used to say, the unknown unknowns. And all that in 30 minutes. Are you ready? Let's go. So let us start by quickly defining what on earth is AI. It's a term slapped onto almost everything these days, from cars to washing machines. My favourite definition is this one, from the late great Larry Tesler. AI is whatever machines haven't done yet, which means whatever it is, we haven't yet achieved it. But the very original definition was this, a system to solve the kinds of problems now reserved for humans and improve themselves. Which I formulate as a computer system designed to perform activities usually requiring a human-like intelligence. Now notice that this doesn't specify a particular technology, such as machine learning or deep learning, and indeed this is the route the new EU law is taking in covering pretty much any technology, including the rules-based expert systems that were the precursor to modern machine learning. Now, the fire hose. Just how powerful is this? What we mean here is big data. Now, big data is defined as extremely large data sets. Basically, I say anything too big to open in Excel. But the other thing about big data is just how fast it expands. Now, most big data sets are consistently growing, and they follow Parkinson's law of data. The expression of this law must be managed as a part of any AI design. Now, for me, I mainly play in the big data known as news data. By its very nature, the news aggregates data on the important topics of the day. It is one of our oldest data generators, a measurement device for the physical and social world which recalibrates itself through corrections, fact-checking, and evolving editorial judgment. Traditionally, it is comprised of millions of fragmented and isolated stories, and often with each story only being a part of a larger overall picture. Some very quick stats. Speaking of big data, here at Dow Jones, we have roughly 1.6 billion articles from around 9,000 sources. And 1,000 of those sources go back longer than 20 years. And the data is also in 26 languages. The data is drawn down from the cloud via these three methods, roughly speaking, big chunks, updates, and searches. I call this a massive data sea. And like sailing on any sea, it is really easy to get lost and there are winds to blow you off course. Which brings us neatly to some of the problems with AI development of big data. Now, working with such large, complex data sets can make data science seem mysterious to those on the outside, and all too often project managers and their designers create a little black box in the middle of their plan, label it machine learning, and leave it to the data scientists. So what is exactly going on inside that box? Well, there are 5 basic stages of any machine learning project: literature review, data exploration, algorithm development, result analysis, final inspection and deployment. And as we all know, it's very smooth sailing from left to right, right? Well, no. Indeed, the stages often go back and forwards as a clear path is established, a process wildly exacerbated where the goal is not clearly defined. In some cases, particularly those with big and complex datasets, there is a risk that teams can struggle with getting beyond the data exploration stages and, in any meaningful way, progress towards a deployment at all. And AI solutions, that is the maps showing the routes across the sea we defined, can be equally massive. This diagram here is the underlying AI architecture for the Amazon Echo. Where would you even start? This is the question I am most asked. Where do I start with all of this? Well, I speak of the elements of success in AI. The key to delivering anything when it comes to AI is to have these three aspects covered. I call this the three legs of the stool. You must have the data in a high enough quality to do something with. Well, great. We have that, or at least we know where to get it. Next, you need data science capability to draw out testable hypotheses and research solutions to them. And finally, and this is the part most often overlooked, we need the business side, the subject matter experts who could provide the essential context for the development to even work. Now, having all three reduces the risk of poor AI development. This risk is contingent on how well the project or the goal has actually been defined. Indeed, it is fair to say that the more significant and most crucial part of the development is actually understanding the problem in depth, assessing the data options, and validating intuitive ideas by hypothesis creation. So the first thing is the translation of a business need into a technical problem. Now, risk is also a crucial concept here. For many businesses, particularly those in the regulated markets, looking at things through the lens of risk and finding ways to do business without adding a risk burden is a critical operational challenge. For a lot of people, they worry that AI is coming to take over. For them, the risk is what we call the uncaring computer. And this is the sort of risks people like the CEO of Google here talk about. As he says at the bottom, it's fair to be worried about AI. Or perhaps the risk is from governing bodies like the EU with its general data protection regulations. Taking this example from that regulation, these three articles show that GDPR is a vital acknowledgement that when algorithms are deployed in society, few if any of the decisions are purely technical. Indeed, the ethical design of algorithms requires coordination between technical and even philosophical resources of the highest caliber. Put into AI terms, these are directly relating to the problems of transparency and explainability, otherwise known as how does it work and why did it do that? Being able to answer these two questions means that AI is likely to be predictable and not dangerous. That brings us to a revolution in AI fostered by a machine learning technique called deep learning. Conventional machine learning techniques are limited in their ability to process raw data, and systems require careful engineering to transform the raw data into a suitable representation. Deep learning methods, on the other hand, are really representation learning methods, which work by composing simple modules that each transform the representation into a more abstract level using hidden layers, hence the deep. With the composition of enough such transformations, very complex functions can be learned. However, this leads to severe issues with explainability. Explainability is the extent to which the internal mechanics of a machine or deep learning system can be explained in human terms. Classical machine learning uses algorithms like decision trees, which gives us firm rules as to why it was decided one way or another. So it is a simple process to map the reasoning in a human understandable form. This is why machine learning algorithms like decision trees and linear logistic regressions are principally used in regulated companies and the banking industry for their ability to explain what is happening. Not only this, but deep learning networks are susceptible to being fooled by data designed to do so. In this example on the screen, images from the left were correctly classified. They then had the noise data in the middle column added, and the deep learning network could no longer classify the image on the right. This is a form of what is called overfitting, and again, the best way to avoid it is to detect and prevent any bias in the original datasets. But moreover, this highlights a fundamental issue with the production of algorithms. That is, as Peter Guy from the South China Morning Post here says, the biggest limitation of artificial intelligence is that it is only as smart as the data sets it serves. And the EU Commission is, of course, watching. Whew. Well, no wonder a lot of companies put AI back in the box at this point, or indeed that the number one implementation of an AI technology is chatbots for websites. Nice and easy, not going to get you into much trouble, probably. So let's see how to best approach the fire hose with some best practices. I call this the solutions-led approach. But what is a solutions approach and why are solutions appropriate for AI problems? Well, I want you to imagine a new technology, one that you need to transform your business to become more competitive. This technology raises the potential for a new competitive advantage. It could be a solution to a problem that has been plaguing your business for ages. A stubborn Gordian knot, which if cut would bring value to your company. Or perhaps it could be something totally new and distinctive, raising the possibility of a new distinctive competence, unique to your business and impossible for your competitors to replicate. Just imagine that, a new area illuminated by an elegant solution, a heady mix of delicate and satisfying mathematics, architecture, vision, which brings around unique value to production, taming the blue sea, turning your business need into a solution. Thinking in solution terms avoids many of the problems we've discussed with developing AI technologies, and particularly where these are big data ideas. We used to say that we could simply dump the data somewhere, swim around inside it, and find valuable correlations. But as I shall show, this is not that easy. The path to true competitiveness is not simply to copy that which others are doing. It is to come up with new ways of your own that are better and different. A proper set of values is the root of a good strategy. This is because the best strategies are rooted themselves in a diagnosis, the analysis of the business challenge ahead, warts and all. From this analysis, you can build a real insight that's actually backed with it. So I'm going to present the notion of humans in the loop being one of the most successful answers to these problems strategically. What does that mean? Well, consider this quote. Who said, technology tends towards the removal of burdens, a burden being something overly manual? I did. And what I meant was that once something becomes onerous and manual labour, then it is ripe for being replaced. This is what we call automation. Now, there are two types of automation. The first is to totally re-engineer a business process and replace it with an AI-led approach, if possible. This is the way automation is commonly used in economics. Once you have built such a system, then you no longer need 90% of the humans currently performing that process, and you can say economic progress has been made. The second, however, is augmentation. This is to change and automate parts of the current process. Thus, you don't fully replace any humans, you enable them to work faster and better by building a system that complements human cognitive capability. This is sometimes called human-machine teaming and is found in AI design where the complex nature of the workflow or tasks actually benefits from a human context when paired with machine learning. Used thoughtfully, AI can augment our intelligence, helping us chart a better and wiser path forward. So let's put this into practice with our fire hose. Here we have a normal, everyday, human-in-the-loop process. We are training an algorithm in the software called Prodigy to be able to determine if a portion of an article is on the topic of innovation or not. Then, within the article itself, we pick off the labels of organizations and people. Now, innovation is a fuzzy concept, and that's why it's best suited to a human to determine in the first instance. We do this by building a pipeline for the training. Starting at the top left, we get out our articles from the system and segment them into paragraphs, before presenting them to the humans. Every article they classify, the algorithm gets more and more sure of itself. So our first step in creating the innovation label leads naturally to our second of improving the built-in labels, such as organization, through the same human-led process. Once we have a satisfactory level of quality, we output the model and run it in Spatie to work on our larger corpus. This human approach is roughly how we do it at Dow Jones. We have developed our processes over nearly 20 years of iterative improvement. Some parts are built for industry-leading speed, such as newswires, which is sub-second, and others are built for aggregation like Factiva Analytics, which includes a lot of metadata. Thirdly, we have a completely evolved blended approach that includes rules-based engines with decades of rules in them, which are curated by dedicated rules professionals. We have machine learning creating footprints to distinguish signals from each other, using technology stacks designed for results rather than being cutting edge. And we have hundreds of expert SMEs, subject matter experts, on every single possible subject of news coverage, all working together as a team to input their knowledge into a workflow system. So humans might be a little slower in training, but they come with many advantages. Firstly, the number of documents needed are themselves thus lower. So if we consider this image here of a feature space, our AI system will try and find the boundary between the circle and triangle spaces. With humans in the loop, you can quickly zero in on the boundary, reducing the number of examples required for the same result. To give a concrete example for the innovation case, once you have a handful of articles with the same sentence structure and vocabulary, and the system has classified those correctly and with high confidence, then you don't need 100 more examples like those. What you need are more examples of articles that the system gets wrong, or for which it has a low confidence. Those are likely articles with a different structure or vocabulary than the system has encountered before. Designing projects like this requires a lot of upfront thinking, and that is the solution-led approach. Those of you with MBAs will probably remember the words of this man, Nigel Slack, when he said that designing comes before construction. So let me describe the stages of our methodology. For years, people have been trying to see inside the box of machine learning development, trying to help data science produce better and safer work, and to be able, most importantly, to connect ideas to action. So many sprint methods, innovation pipelines, accelerator concepts fail at producing data science and data-led projects that land. We used 3 workshops, all supportive of the goal: the problem definition workshop, the solution design workshop, and the data exploration workshop. Note that we are front-loading the problem definition first. For example, in our problem definition workshop, we start with this task: start at the end, identifying our long-term goal. We move on to a pre-mortem, where we challenge all of the dangerous assumptions that we have brought to the project. We then map the current processes before speaking to experts who can define and critique our map. We then collate and prioritize, and we finally select a problem, which may only be a part of the overall. So as you can see, the outputs of these workshops will quickly help see inside the black box and get to that value quicker, potentially saving companies and data scientists suffering from poorly defined problems and solutions. But let us not forget that theory is not practice. Okay, now it is case study time. Our first case study is the perfect example of using AI to bring order to a chaotic event. And what event could be more chaotic and produce more articles than a hurricane? A news story, at its best, contains observations about its subject that are true and relevant at the point in time. What happens when we tie them together, focused around a single event? Our objective then is to gain understanding from a catastrophe. Here was our pipeline. We used the APIs to draw out a snapshot of 97,000 articles. We then pre-processed them for use in the AI. We then processed them again using Spacey to identify entities from the corpus. Now, after only a few hours, we had thousands of entities extracted. We then used the Stanford Library Relationship Extractor, which itself was trained using our product newswires, to structure these entities into triplets, 2 entities and the relationship between them. We then placed these triplets into a graph to be able to map those relationships and then ask questions about the data. That enabled us to work out which entities had high connectedness by measuring their degrees, that is, the number of edges going in degrees, and out degrees, of any one node. High degrees means a greater impact for that node. When zooming out, this gave us a lovely clustered view of the relationships within the graph, as well as the ability to run the graph forwards and backwards in time. Now that we've mapped out the hurricane through the news, we could see that, as shown here, secondary diseases spiked in the region after the event. Or we could also see that the US Centre for Disease Control was heavily involved in the months after the hurricane. We adapted our disease surveillance dashboard to scan for disease terms in the area during the aftermath of Hurricane Harvey. This included picking up the potential for carcinogenic pollution possibly leaking from various industrial sites. So our objective was to make sense of an event through AI-enabled analysis of the news. And we succeeded. We were able to find secondary and even tertiary order effects from the news data when it was placed in a graph. If we were a government organisation planning how best we might respond to future events, this graph would enable planning to be role-played and tested. Such methods enable the productive use of AI to draw value from big data and apply it to almost any situation. Partners of Dow Jones have used similar methods to track Brexit for the government, to track the COVID pandemic, to track and hold companies to account for their environmental impacts, their social responsibilities, and that they walk the walk, not just talk the talk. But this is using AI to analyse the fire hose. What about predicting a big event before it even happens? That is what we'll be talking about in our second case study on horizon scanning. We did this study by bringing together a team during lockdown and used a solutions-led approach over the software called Miro. Here the output from the problem workshop, all the steps and our sprint questions. And here are the solutions, with our workshop designs and the critique. Let's have a closer look at some of the outputs and what we discovered. What are the challenges and problems we can solve? So we discovered how the problem of horizon scanning could be even defined. Of what does it comprise? Well, everyone wants to know the future, to be able to predict it, to be able to react to things before they happen. But what is the future other than the outcomes of the multitude of small events happening now? If only we could see them, these small and weak signals. All too often, we are looking somewhere else entirely, and our attention is drawn by the big events happening around us. However, looking at these big events doesn't help us see into the future because their conclusions are already here. Their time is now. This is the idea behind the 3 horizons model. The concept is that there are 3 types of signals in any timeline. A signal is made up of events relating to a particular topic, and each corresponds to a different strategic planning horizon. The UK Government Futures Toolkit describes Horizon 1 as the present. These are the critical issues happening now and being responded to via current processes and strategy. Horizon 1 trends may eventually wane, however, and be overtaken by the more medium-term Horizon 2. These signals grow into their prominence. Think of something that will happen next year or within the next 5 years. The seeds of such signals are already here, and it is a significant strategic move to plan for them. That leaves us with Horizon 3, those small pebbles that are moving gently and slowly but will eventually form together and become the avalanche upon which the future will be developed. Horizon 3 signals are potentially the most important in the long term. If only we could see them. Think of the rise of the internet and the cloud. These gigantic, impactful signals come from smaller events, which sometimes stretch back for decades. For example, take artificial intelligence itself. So what exactly is a weak signal? The concept goes as far back as the 1970s, with various academic papers from futurologists debating both their nature and of what they comprise. For our purposes, a weak signal has the following definition: a series of events relating to a developing topic that persists, but has notable low visibility. The first key element here is that the signal persists. This differentiates between a weak signal and a wildcard. Wildcard events appear, grow, and then disappear. They do not persist, and represent a short-term trend that is not something to strategically plan for long-term. The second element is that the weak signal pertains to a topic. The introduction of topics brings in a new and essential dimension, because topics, like signals, have a life cycle that we need to incorporate into our thinking. This is related to where the topic can be found. A new topic, one that will form, say, a weak signal, will likely not be found in the mainstream press yet, as it hasn't reached widespread awareness. In 2002, the concept of an information life cycle was adapted by Chun-Wei Chu. This proposed that topics initially appear in specialist sources, such as journals, patent applications, academic papers. They then start to interest in elite groups, formed of, say, analysts or trade journals and business leaders, before finally reaching widespread awareness through radio and TV programs, fictional works, newspapers, and popular magazines. The hype then increases until they become to the attention of governments, who debate and create policies, professional practices, and even educational curricula. For example, AI started in military and science fiction circles, and then moved to specialist statisticals and mathematical spaces before it got picked up by IT experts who applied machine learning to the problems. From there, early business wins meant the topic rose in prominence, becoming a story on the lips of entrepreneurs, newspaper pundits, and now has a broad public awareness and is in the lap of governments to legislate. The journey of a weak signal to becoming a strong signal relates directly to the journey through this topic lifecycle. Our example solution was pretty cool. We took 100,000 articles spread over, say, a year, out of the system, broken into mainstream and specialized press. Definitions we would have to clarify, but Dow Jones has tools to help with this. We then split them into slices, time slices. Each slice contains a certain amount of articles. We then model the topics using NLP, natural language processing technologies, and group those topics into clusters. There are some incredible papers out there on the grouping of topics based on a collection of terms representing that topic. A concept known as zipping allows for the terms making up the topic to change over time as topics evolve, especially over years. Now, the first problem we come across then is how do we know that two articles are about the same topic? Well, as the great linguist John Firth said, you shall know a word by the company it keeps. And that enables you to know the difference between an apple and the Apple company. A collection of terms then makes up a topic, and distinguishing them is simple when you consider their footprint collectively. We then set the horizon period, and we ask this: can we find the same topic, or children thereof, within the subsequent slices? Now, an important point here is that the spacing between these slices is based upon a frame of reference that went into the search, which pulled out the original articles. If the topic persists, it is considered to be part of a chain, and we can use where we have found the topic to be a way of determining where it is on the topic lifecycle. So a topic is a specialized press chunk, will likely be an early signal. Moreover, creating a large volume of topic chains enable us to use them to train a classifier to determine how likely it is for any discovered topic to persist into the future. We could use features such as the number of documents with that topic as a value, the frequency of the topic relative to total numbers of topics, and so forth. Once we have calculated such metric features as the average relative term frequency for all the slices in the data, we can show the difference between a weak and strong signal as the rate of change. Shown against the frequency, this helps draw a difference between the two types of signal, giving us our topic map here on the right, as well as the life cycle here on the left. We would push all of these values to some sort of interactive GUI, so a topic that is currently a weak signal but that will eventually turn into a strong signal can be identified before it will do so. This enables us to predict if a topic is due to become all-conquering. We ran this for the topic of blockchain, and, well, I wish we had designed it earlier, as I would have bought quite a bit more crypto. So that's drinking from the fire hose, and I'm going to leave you with 5 takeaways of best practice for NLP on this topic. First, plan by clarifying ways the problem can be simplified, including planning to include tolerance for inaccuracies. The best advice with designing an AI project is to have a very iterative workflow, working from the general to the specific, seeing what works and what you can get a model to learn. Often this will surprise you and probably disappoint you in equal measure. Second, it is not possible to predetermine the accuracy you're aiming for. This follows from the hypothesis testing. Exactly how much data any given problem requires is dependent on the problem itself. The key is to have consistent and clean data, or you could consider adding in data from a third place, such as a knowledge base. For model architecture, it is important to have a reduced amount of technical debt, to consider not just how to scale up then, but to ensure you can actually scale down to smaller tasks within the project. And it's the early decisions that make that difference. When it comes to optimization, this part of an AI project is often mistaken for the part that moves the needle into production ready. However, as I think we have shown, it is earlier in the project that the difference has been made. Work the problem. That brings us to the end. Thank you very much for listening this far to my presentation of drinking from the fire hose. If you have any questions, please contact me via email.